Assalamu alaikum. So last time we talked in the image segmentation lecture. Last time we talked about region growing, region splitting and merging, and graph cut algorithms. Now in this lecture we will mainly focus on the evolutionary or optimizational algorithms which are used for image segmentation. So let's check the details of those. So one of the method is the active contours or the snake uh, algorithm, and we are going to continue on the concept of image segmentation, and the specific thing we are going to talk about in this lecture is called snakes, also known as active contours. And we continue talking about, I will just give an abstract concept on the level sets following the snakes. So the philosophy behind this material is that everything we talked about so far in terms of segmentation has really been at the pixel by pixel level, right? So we threshold and we get a set of pixels, or we uh, graph cut, we get a set of pixels, right? But as humans, our natural inclination is more about kind of like, if I told you to isolate something in an image, you probably wouldn't click on pixel by pixel. You would probably draw like a freehand contour around the object, right? You think about things in terms of shapes, and so that's the philosophy. Is instead of talking about like pixel level segmentation, we are going to talk about kind of curve level segmentation, and the curve is going to be the key concept that we kind of talk about in this lecture. So let's first see a MATLAB demo on this. So previously we talked about the image segmenter app. Now let's see if I have a kind of an image. Let me show you the image first. So this is the image we have read. Now let me open the image segmenter. Now this is the app we used last time for the graph cut. Now this time we will use it for the active contours. So this is the image we have. What we will do is we will first draw the region of interest, like a freehand thing. So it's like this, and it's like this. So it's like a freehand, so I can just try to draw like this, like something like this. Okay, once we draw, we apply it and we close the ROI, and then we use active contours. So in this contour, let us use 300 iterations, and there are two methods actually, region base and age base. So age base method refers to the geodesic active contour, and region base is referred by chain V's. So let's just evolve it. So as you can see, as you evolve the method, it is trying to stick around, or it's like a rubber band which is trying to stick to the edges around the hand. So this is how the segmentation apply, and if you will apply, this is the segmentation you get, and you can see the active contours here. So this is the binary image. Now consider this, that if we use age based method, let's close active contours and let's just load. Let's just again fill ROIs. This time it's more of a like freehand thing. And we apply and then close the ROI, and then again active contours, but this time age based, and we use it. So see, with the age based, it's a kind of a more sophisticated, so it's slow but it's evolving. I will discuss with you the difference between the age based method and the kind of region based method. So age based methods are more like of level set, not level sets but gradient vector flow, and but they have their own kind of pros and cons to it. So let's say I increase the iterations to 800 and then I again evolve it. So you will see that it requires more number of iterations, and here you can see that the number of iterations has been counted. So let's wait for number of iterations to be. So just see here how it is trying to fit itself within between the fingers. So what it is trying to do is it's trying to like kind of shrink itself between these fingers based on the age gradients. So of course, if I will just add more iterations, I will get a more sophisticated segmentation in this case. But if I just see the active contours here, so this is the result for this. So let's just look to the details that how can we implement this. So snakes are a kind of a parametric representations of a curve. For example, that I have a function of x and y and a parameter s which goes between 0 and 1 continuously. As we change as smoothly, I trace out the closed contour in the plane. So the main idea is to segment using curves, not pixels, and we want segmentation curve that conforms to image ages and is a smoothly varying curve versus lot of jagged nooks and crannies. So in this case, for example, I can see something like this. So if we have uh, the image which is x and y, and if I just make a parameter s, so what it does is it kinds of uh, shrink itself to the age gradients here as it is doing, and it is represented by this, which is the function of x and y, and s is goes between 0 and 1 continuously. So the equations, I can say something like the equations above. It's like if we represent it in this case, so s goes from 0 and then it goes from 0 to 1/4 and then 1/2 and then 3/4 and then again back to 1. So it's a kind of a continuous change, and this is the equation where we use the parametric space rather than the Cartesian coordinate system. And if you remember, in the Huff transform we did use the parametric space because in the Cartesian coordinate system there could be some lags or there could be some problems when detecting the lines and when detecting the edges. So in this case, if I use the Cartesian coordinate system, in this case if I do not use the cleaner version, so I have to look around one more parameter, which is the r. So after the Cartesian thing, this is the way we are going to represent our closed curves, and I am gonna assume that everything we are going to do is a closed contour. So it is possible to have kind of like an open contour, like an arc that is conforming to the edge of some object, but conventionally when we think about the snake stuff, we think about this as closed group. Okay, so also the underlying assumption is that every variable is continuous. Forget about the pixel grid for now, just assume that all the variables are continuous, even the x and y, just for the sake of theory. I want to find the energy of this curve, and then I am going to try to evolve the curve, drive the curve to have the minimum energy, and this energy intuitively should reflect how good is the snake. So let's look at the energy functions, that what kind of energy we are dealing with. So don't freak out on the mathematics, I'll just explain it to you intuitively, not with respect to the derivative and all that stuff. You can, if you are interested, you can go through Gonzalez and Woods. There are 50 pages dedicated to only just this kind of algorithms, so you can look at that, but I will just explain to you intuitively that how this works. So we want to define an energy, let's say E of C, that matches our intuition about what makes good segmentation. Curves will iteratively evolve to reduce, minimize this energy function this. So we have kind of two energy functions. One is internal energy and the second is external energy. I am going to decompose this energy into two parts, as I said. So the internal part is something that only depends on the shape of the curve. So the idea is that independent of the image, how nice is this curve? This is going to encapsulate the idea that the curve should not be too squiggly, too wiggly. So this is kind of saying how good is a curve, like this. So we want the image at the left side, not the right side. Whereas the external energy balances out the function which depends on the image intensities, for example, the edges in the image. So it's a kind of a trade-off which balances the goodness of the curve versus the fitting with the image edges. And as you can imagine, there is a kind of a parameter that I can use to say which one do I think is more important. So let's talk about the internal energy first. So the idea is that we want shapes that kind of minimize the energy of the curve, like how much energy is required to keep the curve in that state. It's like an analogy to a rubber band. If you keep it on the table, it requires zero energy to stay there. But if you try to squeeze it into some sort of weirdo shape, it's going to be like super stretched and there's going to be a lot of tension, and it takes a lot of energy to maintain that tension. This is like the super hand wavy way of thinking. The analogy is simple. The relaxed shapes have lower energy and bendy twisty shapes have more energy. So it is a way to make sure that all things being equal, I have low energy. Those of you that are more physics inclined than I am can think about this in terms of actual tension. I'm not a physics guy, but basically it maps exactly onto the concept of how much energy there is inside a physical object. Like imagine that you have got like a metal hoop that's very flexible, that you could suppose you have got like pegs on a board. You have got this bendy metal hoop and you could either thread the metal hoop around the pegs that would like to have this kind of internal tension, or you just put on the table that would have a very low energy. So the idea is you can use the physics perspective to think about it in that way, but here we will take a maths approach to understand the concept. So how do I encapsulate this concept mathematically? So this is the equation of the internal energy. I know it's a kind of a difficult, but let me explain it. So the first term here kind of refers to how stretchy the curve is or how much tension that curve is under. This is also referred to as the elastic energy of the curve. A low value of the derivative means this is not too stretchy. Basically this kinds of keeps points on the curve together as a function of s. What that means is that as I travel around the curve going from like s, let me just, okay, so this is like if I have these points and they are kind of irregular, so this is like as I go from s equals to 0 to s equals to 0.05 or 0.1 and so on, I don't see the distribution of those points around the curve to be non-uniform, to be too non-uniform. In some sense, ideally, I kind of want to be taking an equal step in arc length of the curve for every little increment to test that I go, so I don't want the points on the curve to be bunched. Now in this case they are bunched, in this case they are irregular, so you can see here there is a problem. Second part of this equation is basically saying that I want a lower double derivative. What that means is that the curve is not too bendy, so basically this term keeps points on curve from oscillating, and that's going to kind of prevent me from being in the state down in the right image. The double derivative of the curve is kind of related to basically the curvature, meaning at every point instantaneously I can think about what is the radius of the circle that sits adjacent to the curve, so that could be negative or positive. So in this case, here it sits adjacent to the curve, here it sits adjacent to the curve, but here it's inside the curve, or here it's inside the curve. So here we can see that I want to know that the radius of the circle, either it sits uh, inside the circle or outside the circle. So it may be negative or positive in that sense, depending whether I am inside or outside. So you can imagine that, in a curve like this, as I roll this little circle around the curve, it's changing radius to match the nooks and crannies of my shape. Whereas with the image on the left, if I just draw circles to the adjacent, so basically they are all inside, or they are all like outside. So it's a kind of a homogeneous thing. So as I roll this circle around the interior of the curve on the left side of the image, because there is not a lot of inlets and islands for this curve to have to negotiate. So this basically is our intuition that I don't want to have lots of squiggles in my curve. In simple words, the first term of the equation says not too stretchy, and the second term says not too bendy. Most of these terms are important because just the shape by itself doesn't necessarily tell me, for example, where the point is along the curve. I could have different parameterizations of the curve that trace out the same path but go along that path at different speeds. So now the question is, what makes the curves good externally? Now we have to make the curve fit with the image edges. Okay, so the intuition is that the curve basically lie right on top of the strong edges in the image right. So in the equation, I got my image assuming that it is to be grayscale. Now we are talking about this, so I am assuming now my image is grayscale, that is I. At every point along the curve S that corresponds to a point xy in the plane, I then evaluate the image intensities, more specifically image gradients at that point. I integrate around the curve, adding up all those gradients. The intuition is that I want this energy to be really low, this particular energy, because if I expand this, I get this, that is the derivative in it's like the gradient in the direction of the x and the gradient in the direction of the y. So what I want is this energy to be really low when I have got edges, right? So let's suppose there is no edge at a given point. That means that the gradient is 0 for this whole point, and that means that at the set point this number inside will be 0. So when I am in the middle of some flat region, nothing's happening. If I have a big edge, then my gradient magnitude is going to be big, and then the number inside will be a big negative number, which means that the edge is going to make the cost function overall have lower energy. So overall, if I take the internal energy plus the external energy, I could get some negative numbers. In simple words, I want the snake to be attracted to edges. Now the second thing will be how to minimize these energies. So of course it requires variational calculus, and that's why I'm not going into the details of that calculus, but if you want to study more, just go through the book Gonzalez and Richard D. Woods. There is a whole chapter dedicated to it. So in practice, for digital images, we solve the problem by creating a curve C of st where s and t are both discrete. So the curve approximation by k discrete points can be given like this. So this is at s equals to 1, s equals to 0, s equals to 2, and this is s equals to k minus 1. Here t refers to the temporal evaluation of the curve. We step c s t minus 1 to c s t by taking a step along gradient of e. Now note that if we just take into account this, what we have to do is we have to like match the lines with respect to the points which we have got with respect to s equals to 1 to k minus 1 at each time step with respect to the gradient. So in practice, this results in 2k by 2k linear system solved at each iteration, that is bunch of finite differences. So the curve inches along the boundary until points around parameter stop changing. So lots of bookkeeping behind the scenes. Now let's see a demo here. Let's discard it. Let's see a demo. So this is one of the algorithm for snake, and you can find its implementation on this link. So you can follow this link to get this code. So I'll just run the GUI here. So once I run the GUI, I have this interface opened. I can load the image. Let's say this one. And what I have to do is I have to set my initial points, let's say like this, and I should start. So once I start, you can see that it's evolving and it's nicely shaping to the circle here, and the iterations are performed. So you can actually vary the iterations. So here the maximum iterations are 200, and if it stops before the iteration, so this is the criteria which is given. And there are some other options like here: size of local energy window, curvature threshold, continuity weight, curvature weight, and gradient weight. So you can actually vary these parameters to see whether which suits you best. But what I want to show you is the problem here. So let's see, I set the new initial points. So I set the new initial points more of a like this way. Now if I start it, you can see that it will not cover the whole circle, but it will just only cover this particular area of the circle. And this is the problem, that it depends on the initial points which we have got. Now let's see if I set another set of points. So let's see, I set it inside the circle, and you will see that it will not converge to the shape of the circle. Now if I just go far enough from this edges and I start it, you will see that it will converge up till now. But at some points, if I just go further beyond, like at the edges of this, let's see what happens here, and I start. Okay, let me just define it again, because I went out of the grid maybe. So here I have made bigger farther away the points, and you will see it still gets some. Let me just load. Okay, let me just load again this one, and let me just get a real world image, because it works on the circle very well. But let's see if it works here. Now you can see that it has stopped at iteration 22, and it doesn't get the results as good as it was getting with the circle, because that was a black and white image and the gradients were too strong. Now let's see if I can get it better with the initialization of my curvature. Now still it does not get a good result in this case. Similarly, if you have the hippie again and you kind of give the points to it, and you start, still you didn't get the results which you were expecting. So that's the problem when we deal with snakes. So let's look at what are those problems. So the problems with basic snakes is that contour never sees strong edges that are far away. So in this case, if you just draw a kind of a contour here, now here are the strong edges, but it doesn't see any strong edges here. Here it's a void for it, and there is no change or there is no gradient here. So that's why it just fails to kind of parameterize that kind of area where there are no gradients. Second problem is the image noise. So image noise creates many small gradients and snake gets hang up. So the possible solution to this is blur image first and then kind of apply this basic snakes. Now this is actually done by gradient vector flow. So the idea, instead of using exactly image gradients, we create a new vector field over the image plane in terms of v, and this is the equation of the v, like v in the direction of x and in the direction of y, and the e refers to the edge map. Now again, don't freak out with this equation, let me explain it first intuitively. So v is actually what we want to do is we want to minimize v. The intuition is, if the gradient of e is big, that means, okay, let me just explain the equation first and then I'll get back to the intuition. So this term here is the magnitude of the edge map, and this term here is the similarity between the vector flow and the edge map, the gradient magnitude of the edge map. So what we want is, if the gradient of e is big, that means that the gradient is large and v is going to follow this edge gradient faithfully if the magnitude is large. If the gradient magnitude is low, it's like if it is very small, then v is just kind of following along to be as smooth as possible, and the responsibility of making the vector flow smooth is done by this equation. So this refers to the smoothness of v. It's a kind of it kind of works as averaging filter, and this here is the tuning parameter which suggests that how smooth the vector field is. Now this mu trades off kind of this mu is a kind of a trade-off as to how smooth I am versus how faithful I am. So it depends on the gradient magnitude. So if the gradient magnitude is large enough, it will be like how faithful I am, and if it is small enough, then it will control kind of the smoothness of this vector field. Now another method which is very popular in this case is level sets. So instead of parameterizing curve by a set of ordered points, discretize image plane xy and define a function phi, and evolve this entire function pixels where phi is equal to 0. Now in this case, what we want to do is we want to check whether our point is onto this curve, then it will be 0, and if it lies inside the region, it will be less than 0. If it lies outside the region, it is greater than 0. So it all does is it assigns the unsigned distance functions. I'll not talk about that in detail, but I will just explain you the intuition behind it. So what it does is it implicitly defines the object contour we care about, like through multiple points or holes, and it follows the curvature at xy where it is actually equal to 0. So at the curvature line, the phi of xy equals to 0, and the phi of xy is defined as x square minus y square minus r. So you can see that if the phi of xy is equal to 0, this term, that is square root of x square minus y square, will be equal to the r, that is the radius. So what it does is, if you will see in the animation, the evolving of the level set function is mathematically very better behaved, and I can add t to evolve it at every time step. So everything I talked about in this lecture are age based, and in the absence of ages we can actually use the region based information like this. So you can see that as you will increase the distance function, you will get the image as a whole. So it's like this will kind of expand, and if you will shrink it, if you will take the smaller distance functions, then the level set will shrink out and it will just focus on this particular area here. So in this case, this gray thing is a kind of the curvature, and the phi is equal to 0 around here, and if phi is less than 0, then this is the bottom thing which you are visualizing here, and if phi is greater than 0, then you get all of this. Now let's see one of the examples of level set. So basically there is a good implementation of the level sets here. So you can go to this particular website and you can just choose new input. Let's say we choose this, and see here we have length penalty u equals to 2. So if you increase it, it will add more blurriness, and if you decrease it, it will make it less blur. So let's increase it here, and we run the algorithm. So here you can see the evolution, that how it is actually evolving, and you can see the segmentation, and you can just apply it to another input. Let's say this, let's and run it. Okay, so see the evaluation and see the regions here, how they are actually evolving, and this is the segmentation map, and this is the input image. So you can see the segmented map and the input image. So you can just try out with different images here. You can use this link. Similarly, you can just see this demo here for the 2D level set and see that how it is kind of evolving. So it's a kind of you see optimization problem. So if you see more optimization problems, you will see that it's a kind of evaluation process, iterative process, that with every iteration it kinds of shrink itself to match the gradients, to match the image gradients. Okay, so let's check some more demos with the MATLAB. So MATLAB has different functions. Let me just clear it. So MATLAB has different functions to it. So let's see one of the examples. So let's see if we have this kind of image. So what we do is we select the mask, and assuming that we do not have any prior knowledge, so we generate the mask like this. So this is our initial control location, and after 100 iterations we get this kind of result. Now of course, if we increase more iterations, it will yield a better result like this. If we increase the iterations, we get this kind of result. So it's perfectly segmented. Now this is the command which you use, active contour, and active contour is basically based on a kind of a combination to the basics next and the gradient vector flow. Now another way to do it is to draw the rectangle by yourself, like we discussed in the class. So let's say we have this kind of hand, and we want to, let me put it here. Okay, and we want to draw the rectangle. So here we draw the rectangle, and once we draw the rectangle, we consider it as a mask, and we just use this active contour to get the results. And you will see that you get this result with this image. So this is the segmented image. Of course, it's not good enough, but still it's something to have if you are working with age based methods. Now another example is the geodesic active contours, which I told you it is an age based method. So let's see one of the examples of age based method, which is geodesic active contours. And let's see the image which we are dealing with. So let's just first select the foreground. So this is selected as the foreground, and let me select something regarding the background. So this is selected as the background. We will create the masks for both foreground and background, and then we apply the geodesic active contours. And once you apply it, you will see the results as this. So this is the foreground and this is the background. So it works on the age intensity levels here. Now similarly, there is also one more method, which is fast marching method. So if you just use that fast marching method, you will see, let's say this is the image, and I create a false mask basically, and I use a weighting mechanism to cut off and a threshold to get the binary response. So you can see the segmented image, and this is the segmented image, and this is the geodesic distances of that image. So as you go this way, so you can see that the edges are quite distinguished here with respect to the geodesic distances. So these are some of the examples for image segmentation and how you can perform them in MATLAB. So there is another category of basically segmentation, which is semantic segmentation, and that's based on the deep learning architectures. So basically what semantic segmentation is, it's not just the segmentation, is object based segmentation. So what you do is you recognize the regions, you recognize the objects, and you segment them accordingly. So in MATLAB there is a demo which is available. You can go through it and you can perform such kind of semantic segmentations, where you can semantically segment the wall, the vegetation, the tunnel, the cars, the truck, the bus, and all of that. So this is some of my works. I did the semantic segmentation on different images, and here are some of the results. That can actually segment the horses and the cows, that can segment the cats and the dogs, that can segment different types of vehicles like motorbike, plane, and the human, and that can segment this kind of stuff. So semantic segment, we will talk about semantic segmentation when we'll discuss about the machine learning and supervised learning thing. Maybe I'll explain you some of the aspects, but for now semantic segmentation is based on supervised learning, where you actually kind of segment the objects or the regions which are actually labeled. So there is no unsupervised element to it, or there is no semi-supervised element. This is completely supervised technique. So please leave your questions in Google Classroom, and if you have any questions you want to discuss in live sessions, please discuss them. I know there will be a problem in understanding mathematics, so in the live session I'll explain you more about those mathematical terms. Okay, till then, goodbye.